Alright, so we're going to talk about electric forces, fields, potential, all sorts of different things. Some of the words you may have heard before. Okay? Did I skip a page?
Yeah.
Oh, yes. Okay. So, electric charge, it's a fundamental property of matter. So we've talked about some fundamental properties of matter. Or really, we just talked about one fundamental property of matter. The one we talked about before was mass. That all objects, all matter is made up of stuff. And we describe how much stuff that is as mass. In a similar way, all matter has charge. It's a fundamental property of matter, along with mass. It can be positively charged or negatively charged, or often it's the case that it has equal numbers of positive and negative charges, and so we say it's neutrally charged. The unit of charge, the fundamental unit of charge, we call an E, 1E, and so we often use that to describe how much charge an object has. And 1E is the charge of one electron or one proton. You should have had this, gosh, you probably had this in middle school even. The unit of that is the Coulomb. So the SI unit is the Coulomb. So just to be clear, when I say the fundamental unit of charge, that doesn't refer to the unit that like goes after the number. It just means what is the fundamental parcel of charge. How do we divide it up? And we divide it up in units of the charge of an electron or a proton. They both have the same. Make this bigger. 1E has a value of 1.6 times 10 to the minus 19 coulombs. Hey, good morning, Alan. Here you go. That's right. By the way, the exams are on the website. I just posted them this morning, so you can go and figure out which one it is.
Is it a lowercase c?
It is a uppercase C, because it's a person's name. It was a scientist, 1800s, I think. So the charge of one proton is 1E. The charge of one electron is negative 1E. And then the charge of one neutron, which is a neutrally charged particle, is 0E. And so one proton, we could further say, it has a charge of 1.6 times 10 to the minus 19 coulombs. Those are the same, right? To say 1E and this value, those are one and the same, because the fundamental unit of charge has a value equal to this. All atoms have charges, but most are typically neutral. But we do have some atoms that are charged, and we call those cations or anions. Cations are positive. They have a net positive charge. That means they have fewer electrons, and this is the symbol that we often use for electrons, E negative. Let me go and put a little clarification there. That means electron. They have fewer electrons than protons. And the symbol we use for protons is E positive. And then anions have a negative charge, and they have more electrons than they have protons. So an anion, for example, or you tell me, if I have an atom, the nucleus is made up of that many protons, and then it's surrounded by electrons. What is that? Is that a cation or is that an anion?
Anion.
That's an anion, right, because it has 5 electrons and 4 protons. Okay? And if I had more protons than electrons, it'd be a cation. Atoms become charged by removal or addition of electrons.
So there's no
No, it is a superscript, like an E with a negative up high. like a squared.
No. After the word good, still call that.
Right here?
Yeah, it's more electrons than protons.
Oh.
Yeah. Yeah. You want me to write that? More electrons than protons. Thank you, Vanessa. All right. Atoms become charged by the removal or addition of what? Electrons or protons?
Electrons.
Right, electrons. Because electrons are easy to strip away. Yeah, they're just not very tightly bound. We'll talk about this in the very last chapter, in our nuclear chapter. That's when we'll talk about how atoms can change by shifting around protons. But for now, we're just going to talk about atoms becoming charged by the removal or addition of electrons, not protons. It's very difficult to get rid of a proton, but it's relatively easy to take or give an electron. Okay? Yeah, I like it. Charge is quantized. This is a property of charge. Charge is quantized. That means it comes in particular quantities. Okay? That I can have one charge, or I can have two charges, or I can have three charges, but I can't have 1.5 charges. And when I say charges, what I mean is I can have one electron, or I can have two electrons, or I can have three electrons, but I can't have 1.5 electrons.
That's a Q.
That's a Q, man. Yeah, so it should come out a little wider. So charge is quantized. That means that I can have plus or minus 1 E. I can have one electron or one proton. I can have plus or minus 2 E, plus or minus 3 E, and on. But I can't have anywhere in between. I can't take the charge of an electron and split it in two. Okay?
Is that where the levels come in?
No.
No.
All right. I don't know that we're going to get to discrete energy levels, but you're right that in an atom you have discrete energy levels. I forget if we get to that in this chapter. I don't think we do. Now this is just if I have an electron all by itself, not part of an atom, I can't take that electron and chop it in two and have two half electrons. The conservation of charge says that we do not produce or destroy charges. We can only move them around. All right, let's try some of these questions here. No, that's not it. So it's the charge is quantized. It's just a basic property of charge.
So it isn't.
Huh?
It isn't shorted because it's part of the part.
Okay, yeah. All right, positively charged atom, what is that called? Pion, anion, cation, or is it a gluon? All right, just a few more seconds. All right, somebody's not clicking in, but I'm going to go away at 58, okay? Check to make sure that you're on your AA frequency. Okay, good. C is right. It is a cation.
Are the other two really a thing?
Right, yeah, they're like nuclear particles. Right. And the gluon, yeah, they're both things. Which of these is not a valid charge? Remember that the fundamental unit of charge has a value of 1.6 times 10 to the minus 19. And the fact that charge is quantized means that that cannot be further subdivided. It can't be cut into two halves or thirds or whatever. I can't get a quantity that's any fraction of 1.6 times 10 to the minus 19. So, for example, I'll tell you the answer is not A. Because if I look at A, I can tell that this is, first of all, are they protons or electrons discharged?
Protons.
They're protons because it's positive. And how many protons? What times 1.6 is equal to 4.8?
3.
Right, 3. So this is 3 protons right here. So look at those others and ask yourself, are those integer or are those equal numbers of protons or electrons? Not equal. Are they quantized? Discrete numbers, I guess, of protons or electrons. All right, let's stop at 1:30. Okay, so let's see. So when we put B is negative, and that might be why you put B, because it's negative. But the negative just means that what? This is electrons. So it doesn't mean that it's not a valid charge. This is something that can occur in nature. What you really want to look at is this number. And 3.2 is how many electrons? It's 2 electrons. It's 3.2 divided by 1.6, or 32 divided by 16 is 2. This is 1 proton. What is this? I know that 3 protons is 4.8. 4 protons would be 4 times 16 is what? 64, 6.4. So this is between those two. So that's not a valid charge. So D is the right answer there. Okay? So you're looking to see which value is an equal number of these values. Okay? Huh?
I put B at first because it was negative and then
Yeah.
I changed it.
Here. All right. Okay, so electric force. This is going to be, pretty foundational to what goes on in atoms. We observe electric forces between 2 or more charges. And forces always require at least 2 bodies. Right, because we say that if we have one force, then we have another force. There isn't a force that doesn't require 2 bodies. You can't just have a force exert a force on itself. If I push on a wall, the wall pushes back on me. If the Earth exerts a gravitational force on me, then I pull back up with an equal and opposite force. So I always require at least 2 bodies for a force to occur. And then Coulomb's law describes this force. We've seen something very similar before. Let me just write Coulomb's law. KQQ over R squared. And here, Q, I'll call this Q1 and Q2. Those are my 2 charges. So I have 2 charges right here. They're going to be separated by a certain distance. That's going to be my R value. Excuse me, let's, usually I use R, but your book uses D, so I'm going to change that to D. This is my distance D here. Those are my charges, Q1 and Q2. Remember, those are measured in coulombs. That's the SI unit. And that's it. K is a constant. It's called Coulomb's constant.
So the K and the Q's are all over D.
Yeah. KQQ over D squared. It's over D squared. We've seen something very similar to this before. We saw the universal law of gravitation. I'm not sure if you remember, but we just sort of spent a brief amount of time on it. GMM over R squared. If you recall, that described the gravitational force between 2 masses and the distance, which I think we call it this G, but it's just the distance between the 2. So these are very similar expressions. The reason that they're so similar, and you see these types of expressions, these inverse square relationships a lot. We said this before. Do y'all know why? Why do you see inverse square relationships a lot in nature?
Just think of the balance each other.
anything. What was the inverse square relationship?
The spherical nature.
The spherical symmetry, right? So spherical symmetry, and the way that forces act over these spherically symmetric volumes causes this type of inverse square relationship to occur. All right, d is the distance between the charges. You're not going to have to actually calculate the force, but I do want you to understand what happens when some of these quantities change. So like, for example, if I increase the value of Q here by, say, a factor of 2, what does that do to the force between the two charges?
Go up.
It's going to go up, right? So if I increase Q, say by a factor of 2, whenever I do these type of problems, I like to write out my equation. If I increase this, say, by a factor of 2, that means this is going to go up by a factor of 2. Whereas if I increase this by a factor of 2, it's going to go down by what amount? That's right, by a factor of 4.
Finally getting it.
You're getting it because I get a 1 over 4 here. I also have to have a 1 over 4 here. Okay? Because it's squared. It's squared. 2 squared. Whatever I do to one side, I have to do to the other side. Those are important skills for you to have, that you're able to look at an equation and think about how the variables are related to one another. If you're curious, don't write this down unless you're just curious, but the value of k is 9 times 10 to the 9. And that's in, what is it? Newtons meters squared per Coulomb squared. But you don't need to know that. I'm not going to ask you that on the test. All right?
So what is the constant of? You might have said this wrong.
The Coulomb's constant?
Yeah.
It's just a constant that relates the force to the charges at the distance. It actually is based on something a little more fundamental, but just think of it as a constant right now. Or just think of it as a constant forever.
Will we understand what Coulomb in this class or no?
No.
That's the right today for what?
Okay? Like charges, unlike with masses, which are always attractive, masses are always attractive. They're always attracted to one another. That's not true with charges. Like charges repel, and opposite charges attract. Yeah, I don't know why people say that. If multiple charges, if you have multiple charges, then that means there will be multiple forces. So for example, let's imagine this force. That charge. What are all the forces that are acting on that charge? Well, first of all, how many forces are there going to be?
3.
There are going to be 3 forces, because I have 1, 2, 3 charges, and they're all going to exert a force on this particle. It's a good test question where I could give you a system of particles like this and ask you to identify what is the vector that describes the force on one of those particles. Let me show you how you do that. You would look at each particle, realizing that Q3 is negative, Q1 is positive, so that means there's going to be an attractive force. So I'm going to call this F31. That's the force on particle 3 due to particle 1. What about the force due to particle 2? That would be F32. What would be the direction of F32? That is a force on this particle due to this particle. It's going to be repulsive, right? So the force can either be in this direction or in this direction, and it's going to be in that downward direction. Very good. So F32 is going to be in this direction, and then F34 is going to be an attractive force. Now, a way that I might ask this on a test is I would give you, let's say I give you negative, positive, positive, and I ask you, what is the, hold on, let me think what the answer is first.
Robert's the only one that's circle.
Hmm?
That's the one he's talking about.
Let's try this question. Which of these best represents the net force vector on that positive particle? So there are actually two force vectors that are acting on this positive particle, and I want to know which of these represents the sum of those two vectors. Let me show you an example. So for example, if I had, say over here, let's imagine that I did not have Q2, that this particle didn't exist. Then I would draw those two vectors. And then the sum of those two vectors would be something in between it. So it would look like that. So the answer, if this was the thing, it would be that. You follow what I'm saying? If I have two vectors, the sum of those two vectors is somewhere in between them.
So in other words, what's the split?
Yeah, that's the split. Like if you have two guys pulling on an object with ropes in different directions, then the net force on that object is in this direction. And so here I want to know what is which of these forces which of these forces is the sum of the individual forces on this particle right here? Is it A, B, C, or D? There's only one answer that's possible. All right? I'll show you. All right? Just a few more seconds. Let's do about 5 or 8 more seconds. I'll stop at 138. Just guess if you're not sure. By the way, with your class participation, just want to reiterate that the class participation, you need 50% of class participation in order to get the full 50 points. So the value that I put on Moodle, that is the percentage of the total amount of raw points that you can get with your clicker. And almost everybody, I mean, you guys come to class regularly, so almost everybody that comes, like y'all do, have 50% or more. It's actually a pretty low bar. You have to miss a lot of class to not get the full 50%. You're clear with me?
So you're on track to get the full point.
If you have 50% on class participation, yes. All right, let's see here. Oh, goodness. Yeah, A is right. Let me show you here. So the first thing you want to do is to draw your two vectors. I have a force vector here. That's due to this particle. And then I have a force vector here. Then I know that the only possible net force it can be is A. Because, like I said, imagine that I have an object and I have two guys pulling on it with ropes. They're pulling in these directions. Then the net force, the direction that the box is going to move, is going to be somewhere in between. Okay? Huh?
Because I was thinking, like, how is those repelling, and then I realized that's a positive.
Yeah, they're positive. So, you know, in practice, all you're doing is you're drawing these force vectors like we did here, and then selecting the one that's in between. This is like the sum of the vectors.
It's because the positive wants to go to the negative, and it wants to go away from the positive.
Yeah,
So then the sum is just whatever's in the middle.
Whatever's in the middle. Right. It's very simple vector math. But the first step is you ask, what is the force on this particle due to this particle? Since these are both positive, it's repulsive. Here, since these are opposite, I have an attractive force. That's the green arrow. And then, now that I have my two individual forces, I look for the blue arrows, which is the possible net force, the sum of those two forces, and this is the only possible one. It can't be this one because I have this other force vector. It can't be these. They're just sort of in the completely opposite direction. Just looking for that vector that's in between my two individual vectors. That's what we call our net vector, our vector sum. We saw vector sums back in chapter 1 or 2, I think. If you take calculus 3, I think you do a lot of vector sums. Right. Yeah, no? Okay.
Calculus is not my friend right now.
All right. We can calculate the electric force. I'm not going to ask you to do this on the test, but let's just calculate it just so you get an idea sort of what is the magnitude of the forces. So I have two carbon atoms that are separated. Actually, no, we're not going to do that. I don't think it's even that useful. Let's just skip this. Yeah, we don't need to worry about that. No, let's do it. Let's do it. None of the tests, just, I don't know. But I want to illustrate something.
Sure this time.
Huh?
Sure this time.
Yeah, let's not do it. No, we're going to do it. Did you already cross it out?
Yes.
That's what I thought.
I'll go to talk about it.
So that's my KQQ over D squared. If I want to know what F is, that's 9 times 10 to the 9th. The charge of a carbon atom is plus 6e.
Is that the number that's on top?
Hmm?
Is that the number that's on top on the chart?
Oh, on the, yes.
Oh. Yeah, okay. Yeah, it is.
Yeah.
Well, for that one.
So plus 6e, and we're assuming that that's, yes, I guess we're assuming that it's stripped of its electrons. I forget what was going on here. It doesn't really matter right now. But, so that gives me a charge of 9.6 times 10 to the minus 16. Coulombs.
Because it was times 6.
Right. Mm-hmm. And so I can.
That's Q1 or Q2? So
Let's actually. I'm sorry. This is gonna just confuse y'all. We'll just skip this. I am gonna give you the value for the force though. This is not important. Okay. But if I calculate the value of the force, it's pretty small. The force between carbon atoms is like 3.3 times 10 to the minus 8 newtons. So I have a pretty small force between these carbon nuclei. But the carbon nucleus is really, really small. It doesn't have a very big mass at all. Its mass is like 2 times 10 to the minus 26 kilograms. So even though I have such a tiny little force, it causes a big difference in the motion of the carbon nucleus because I can find the acceleration. Remember, acceleration is F over m. That's Newton's second law. F equals ma. So A is equal to F over m. It gives me an acceleration equal to 3.3 times 10 to the minus 8. That's newtons divided by the mass, which is 2 times 10 to the minus 26 kilograms. And so that's equal to 10 to the 18 meters per second squared. So these are tiny little forces on atomic scales, but they cause great accelerations just because everything's so small.
is the 0.5 what would have been the distance?
Uh-huh. Yeah, so a half a nanometer, which is a very small distance. Okay? Now, this is important, and we'll get into this in the body section of this chapter, because the body uses charges a lot, especially in the nervous system. We'll talk about the nervous system and the different cells that are employed in the nervous system. But the body uses electric forces to move cations and anions around. In the nervous system. And that's the context that we'll be talking about. So, for example, if I have these particles between charged plates, we'll think of these as like two metal plates. When we talk about cells, we'll see that cells have different charge distributions on their separate sides, and we'll see how charges will then move back and forth. But for now, we'll just imagine that we have a metal plate over here that's positively charged, and a metal plate over here that's negatively charged. Later, we'll call these capacitors. But for now, we just think of I have a metal plate, and I can put charges onto it, Over here I have a metal plate, and I can put charges onto it. And then I put individual charges in between. So what happens to these charges if I take a positive charge, forget about this for now, if I take a positive charge and dump it here in the middle, what's going to happen to it? What direction will it move? The negative. Right, it's going to move towards the negative or away from the positive, right? I get repulsive forces from the left and attractive forces from the right. So the net motion that it's going to have, the net force, will be to the right. And what about this bottom object?
Opposite.
Opposite, right? It's going to get a repulsive forces from this side. The negative and negative will repel, and it's going to be attracted to this side. So it'll move in that direction. Now let me throw some vocabulary out here. We'll see this. I'll define it in more detail in just a bit, but I want to describe these in terms of potential. And potential you've heard before. You might have heard it in terms of voltage. Like when you talk about a 9-volt battery, then you're talking about the potential that the battery has. Potential is a measure of energy. Particularly, it's a measure of energy per charge.
I thought it was like potential energy.
No, this isn't potential energy. This is something else. It's called potential. Just potential. It's different from potential energy. It's related. It's very similar because potential energy is energy. But this is energy per charge. I'm going to write this again later, but I just want to throw this out here right now. We usually use the letter V for potential, and it's measured in volts.
I don't know how many charges there are.
Oh, we can measure the number of charges. Yeah, we'll talk about capacitors and how those work a little bit later. But we can set how many charges go on these metal plates. Right now, we're just sort of imagining them.
Okay, so we're not talking about like batteries. Like I was saying, like how do you know?
No, this isn't a battery. This is
But
two
for
metal
the,
plates.
So the potential is only for that?
No, I'm getting to it.
Oh.
I'm describing a word right now. Potential is energy per charge. Okay, it's a measure of energy per charge. It's measured in volts. It has your more basic units of joules per coulomb. Energy is in joules, coulomb per charge. Now, if I were to describe the amount of energy per charge, or you can think of it as potential energy per charge, what is the potential for motion for these charges? If I were to describe potential energy per charge for these plates, then the left-hand side would be a high potential. It would have a big value for V. And the right-hand side would be low potential. Right?
Because it's negative.
Because it's negative, yeah. So this is negative, so it has a low potential, and this is positive, so it has a high potential. Don't worry if you're not getting this now, because we're going to come to this topic again soon, and we'll describe it in greater detail. Now, the point here is that charges will move either from low to high potential or high to low potential. We've seen this already when we talked about gravitational potential energy. Imagine you have a mountain and have an object up here. On a mountain, the top is a high potential, and the bottom is low potential. And if I have an object at the top of my mountain, is it going to move from high to low or low to high? It'll always move from high to low. A mass will always move from high to low because gravity's pulling it down. A mass will never move from low to high, right? That would be really strange if you put a mass down here and it moved up the hillside all by itself.
If it does, you know the world's about to end.
Something's going wrong, right?
Hey, have you seen where in San Antonio they had like they call it the haunted railroad tracks because your car would go up the hill, but it had something to do with
Yeah, it's just
lights.
the way that you, the perspective. Yeah. There's a road in England that's similar. It looks like it's going uphill, but actually you're going downhill. All right, so objects will always move from high to low. But with charges, it's a little bit different. With charges, well, you tell me, what type of charge will move from high to low? A positive or a negative charge? A positive charge. So positive charges act like masses act. But negative charges, if I have a negative charge, say over here, it's going to move from low to high. So the negative charge would do the opposite of what the positive charge does.
Well, doesn't it kind of make sense though, because it has to balance.
I don't know, it doesn't make sense to me.
The
but-
positive has to move to the negative, and the negative has to move to the positive. To the
Sure,
negative
yeah.
balance.
But we didn't see that for masses. Masses didn't do that. But this will be important later when we get to cells and we see how cations and anions move back and forth between positively charged and negatively charged. They'll move from low to high or high to low potential. So you'll see this idea again later. Remember, negative charges will move from low to high. Positive charges will move from high to low. All right?
So what if you had more positives on one side? Would it push it further than
No,
the other?
yeah, it would still be, it wouldn't really affect. I mean, it would still move in the same way.
How much is what moving drives?
Okay. Let's try these two. Two positive charges, which are 2 meters apart, experience a force of 12 newtons. You move the charges 4 meters apart, what is the new force in the charges? Remember our equation. F is KQ over R squared. F is 12 newtons when it's 2 meters apart. What happens when you move them to 4 meters apart? Not 4 times the distance, but from 2 meters to 4 meters.
So test 4 starts on this chapter.
Yeah. And it'll definitely get the next chapter. It might get part of nuclear. If we don't get to nuclear, I'm not too upset, but we'll definitely get to nuclear.
Do you teach online?
Not this class.
Well,
no.
no, in class.
Yeah, I've taught online classes, but I don't like
Do
them.
you do it the same? Like, because it was really helpful, you know how you send the...
Yeah, I do that, but I don't like, because students don't do well on it. The pass rate's like 45%. I mean, not in this class. In this class, we'll get a great pass rate. But in an online class, it's terrible. Even with the same delivery of content. Just because, I don't know,
It's harder to learn.
it's harder.
It's
Yeah.
harder to focus at home.
Be very diligent, yeah. All right, let's stop this at 150. I'm about to do it. Thinking about doing a high school online class for CMC, but okay, let's see. So, yeah, A. Huh? All right. So what I'm doing here is I'm doubling the distance, going from 2 meters to 4 meters. Yeah, Kate?
The answer's straight.
Yeah, it was A. I'm sorry. I keep writing R there. I should write D. That's what we have on your equation sheet. I'm sorry. In my other class, we use R because that's just sort of more typical.
R, well, you're using R for like radius?
R is not radius. R is still the distance between the charges. So Q and Q, that's the distance, although sometimes I'll use R. I'm sorry, it's just habit. So if I double the distance, going from 2 meters to 4 meters, I doubled this value, that means I'm going to quarter this value. And so whereas it was 12 newtons, I quarter it, now it's going to be equal to 3 newtons. So that's why A is the right answer. You shall see a question like that where I ask you what happens if you change this value. And then 2 positive particles experience a force that is what? All right, let's stop it at 20. All right, awesome. That's easy, right? But you'll have some like that too. The 2 positive particles experience a repulsive force. All right? The next time we're going to have a field trip. We're going to take a field trip in this class to the old Coke plant that used to be here in Thibodeau. Did y'all know there used to be a Coke plant here in Thibodeau?
No, the sheriff's office.
Yeah, we're going to go there. You better be ready, because there's going to be a pop quiz.
In this class? Or when they're in this class?
That was a joke. There's going to be a pop quiz.
We can go.
All right. I hope there's no pop quiz.
So is there really a pop quiz though?
There's no pop quiz, and there's no field trip to the Coke plant.
Maybe that's the real joke.
All right, electric fields. We've seen fields before. You don't know that we have, but we have. Right. An electric field is force per unit charge. So if you want to think about it, we've seen forces, fields, and potential are all big ideas. Forces are just the forces between two charges. Potential is an energy per unit charge. And an electric field is a force per unit charge. We've seen electric fields before, or not electric fields, we've seen another type of field already. We saw a field that was a force per unit mass. Do you know what that was? What field, what did we call that field?
Gravity.
Gravity, right. So that was our gravitational field. And in fact, when we talk about G isn't an acceleration. It's different from an acceleration, even though it had the same units, and we even called it an acceleration. It's really a measure of the gravitational field. It says if I have an object of mass within that gravitational field, then what force is it going to feel? The field is just a mathematical tool that we use to describe these types of forces. And there's lots of cool stuff that you can do with a field to describe how objects move through that field. So let me describe to you what an electric field is. But in short, it's going to be, you need to remember this, that it is a force per unit charge. Keep that big idea in your head, along with potential, which is an energy per charge, and along with forces, like we talked about, that Coulomb's law.
Curious, I have 3 big ideas that I can turn into a paper.
Yeah, I mean, if you want to do that, that'd be great. All right, forces, fields, and potential. And you could look at them in terms of the body or electrical devices. I don't know, there's all sorts of things you could do. Try not to...
I was very struggling, so
Listen, the project idea is not for a grade, so try not to use what we talk about in class today as your project idea. Try to think beyond that. Okay, so two charged particles experience a force, right? But if you remove one of the charges, the force no longer exists. Like that force just goes away. Because remember what we said, you had to have two bodies to feel a force. You can't have a force without two bodies. But something is still there. Right? We still have the possibility of having a force. If we were to bring in another charge, then we would feel that force again. So we need some way to describe what is there. There is something there when you just have a single charge. And so we use the electric field to describe this something. As I said, the electric field is a measure of force per unit charge, so E is F over Q. It's equal to F over Q. Sometimes you'll see this written a little bit differently as F is equal to Q times E.
Wait, where'd you get Q?
Oh, that's charge. Oh, have I not used that yet?
No.
I'm sorry. Oh, I did. We used it in Coulomb's law.
Oh.
Yeah, so Q is the charge. It's a variable we use for charge. And then often we write it like this, F equals QE. Notice this is a lot like Newton's law. F is equal to mass times G, M times G. The mass is an inherent property of matter, and the G is also a measure of the gravitational field. So it's a lot like Newton's second law, this idea of electric field. Let's imagine right now, don't cross through Q2, but I'm going to imagine right now that Q2 is not here. But don't you do that, because I'm going to erase that, and it'll come back. But just imagine right now that we have Q1. If we have a single particle like this, I would draw the electric field with a series of lines. and it would look like this. I would have lines that would come out radially from that object, like that. And they go out into space and they extend forever. And what those particles, or what those lines show, is the direction of force that a particle would feel if it were in that position. So I imagine that I have a positive particle, and I put it right here, an imaginary positive particle, and I ask myself, what is the direction of the force on that imaginary positive particle? And if this is a positively charged particle, which we're assuming it is, then the force is going to be repulsive. And so if I put an imaginary positive particle right here, the vector, the force vector, would point out. If I put it here, 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 anywhere along here, all those vectors are going to point radially outwards. I'll write that in words in just a second. And so if I imagine then that I bring Q2 back, then the force that is on Q2 due to Q1 is going to be along the direction of the field lines. It's going to be in that direction. These are both positive particles. Let me put some of that in words, okay? Because I said some pretty big things. If we place a charge at a point where there's an electric field, I'm going to call it E field from here on, electric field. It will feel a force, and that force is equal to Q times whatever the electric field is. So here, F21 is equal to Q2 times the electric field due to particle 1. Okay?
Is that why fields conduct that electric field around them whenever you touch them or something?
I don't know how that works.
No.
Okay? The direction of the field is given by the direction that a positive particle would feel a force. So let me if I have a positive particle right here, and I want to know what the field looks like, or let's say I have a negative particle. We can do a negative particle. I have a negative particle right here, and I want to know what the field around that particle looks like. I take an imaginary, let's do green as imaginary. I take an imaginary positive test particle, and I ask what is the direction of the force. And the direction of the force would be in this direction. So that is also the direction of the electric field. And then I move my positive test particle. It's imaginary, it doesn't actually exist, it's just in my head. And I move it over here, and it would feel a force in that direction. So the electric field would be in that direction. And I do it all the way around, and my gravitational field, or excuse me, my electric field would look like that. By the way, that's what the gravitational field of the Earth looks like too, because it's an attractive force, gravitational forces. So the gravitational field looks like that.
So you assume that for a negative, that the other one is positive?
I started with a negative particle right here. And I want to know what is the direction of the electric field around this particle. In order to determine that, I imagine a positive particle. And I put that positive particle here, or here, or here, or here. It's an imaginary thing.
But you always imagine a positive?
Always imagine a positive particle. My physics teacher in high school said you always had to have two things with you when you walk around in your back pocket. One of them was your right hand, because we use the right hand for something called the right hand rule. We're not going to get into that. But the other thing is that you need to always have your positive test charge. So whenever you come to class, you always have to have your positive test charge in your back pocket. Okay? You have your positive test charge?
But how do you know the direction, like the negative not attracting to the positive? I guess that's where I get confused.
Yeah.
Don't worry about the effect of this charge on that charge. Just ask yourself, if I have a positive charge here, what is the force on it? and the force on it is going to be towards that negative charge.
So the negative is always going to look like that. The positive one's always going to look
Hold on
like
just a
that.
second. That didn't
Yeah.
answer your question, did it?
No, because,
Go
I
ahead.
mean, you're saying that the positive goes toward the negative, but why is the negative not the one out?
I'm not worried about the force that's on the negative.
Okay.
I'm just asking myself, if I were to put a positive charge here, what kind of force would it feel?
Right, would attract to
Yeah.
the negative.
And then whatever the direction of that force is the direction of the electric field.
Okay.
Okay?
So the arrows, in terms of arrows, the positive is always going to go this way and the negative is always going to go this way?
I don't understand.
So the negative
Oh,
is always
yes.
going to
So
look like that.
negative particles will always have arrows going in because they're attracted to the positive. And positive particles will always have electric fields going out.
That's, I guess that's one.
Does that answer your question then? Let's see. Yeah. Well, let's do, it'll be like this question. Something similar. Let's try this one. So if Q is positive, what is the direction of the electric field at point A? Is it up, down, left, or right? If Q is positive, what is the direction of the electric field at point A? All right, just a few more seconds. Stopping at 30. Let's guess if you don't know. Awesome. D is right. So it's going to move to the electric field will be to the right. If this is a positive particle, I imagine a positive test particle here, and then that means that the electric field will be in that direction because that positive test particle feels a repulsive force. Okay. Is that clear? Yeah. Okay.
Okay, one more thing. So a negative is always going to go to the positive. The positive is always going to go to a positive.
Yeah, that doesn't make any sense. So,
No. So if I have a positive particle, the electric fields are always like this. If I have a negative particle, it's always like this. It's always into the particle.
so what you're saying is it's pushing A away.
No, there's no pushing. There's no forces. I mean, pushing A away. Wait, what is A? No, A isn't a charge. A is just a point in space.
It's not a charge.
It's just a point. Right, it's a point in space. All right, let's try this next one. An electric field requires what? At least how many particles to have an electric field? All right, it's a few more seconds. Let's stop at 20. Okay, no. The answer is A. So forces require two particles. But fields, remember we talked about how if we have two charges here, they feel either an attractive or repulsive force. But if I take away one of those charges, I still have to have a way to describe what would happen if I bring that charge back. And the field is our way to describe that. So a field helps us to describe what the force would be like if there was a second force. So I can have a field just for a single charge. I can have it for 2 or 3 or 4 charges. It gets more complicated, a lot more complicated. But a field we can use to describe the force per unit charge for a single charge. All right?
So-
Forces require 2 particles, but fields only require 1.
On this other question, if Q was negative,
Mm-hmm.
what would the answer?
What would the answer be if Q was negative? No?
Or left?
Left.
It would be to the left, yeah. So if the particle in this previous one was a negative, and this was my point A, then the electric field would be opposite, yeah. Because I would imagine a positive test charge at point A, and ask myself, what is the direction of the force? It's attracted, so that means that the field is also in that direction.
Gotcha.
Remember, forces and fields are very closely related, right? F is equal to QE. In fact, these are both vectors. So whatever the direction of the force is also the direction for the electric field. And that's why this whole thing works, because the force and the electric field are in the same direction. But it depends on the charge. If I have a positive charge, or if I have two positive charges, they're going to be repulsive. A negative and a positive are going to be attractive.
You see, that right there confuses me.
What about
What
it?
is said about that? It is not explaining those arrows.
I get what she's saying.
I don't understand the confusion. Why don't we talk later? Talk about it later. We figure out sort of where you're missing. All right? All right. So, we can combine Coulomb's law. Remember, Coulomb's law was F kk over d squared, k qq over d squared. And the definition of the electric field is F over Q. We can combine these two in order to get an equation for the electric field. And you don't need to know how to derive this, but it's a fairly easy derivation. I just say that E is equal to F over Q, and that's going to be K QQ over D squared divided by Q. And so that gets rid of one of my Q's, and I'm left then with E is equal to KQ over D squared. It's on your equation sheet and all that. You don't really need to know where it comes from, but I don't know, it's kind of important to know that electric field is force per unit charge, and that this is force, and then I can do this little step where I get an expression for the electric field. Okay? It is on the equation sheet right here. So how does the electric field vary with the other variables? Just like we did with Coulomb's law. If I increase Q, what does that do to the electric field? And if I increase the distance, what does that do? If Q goes up, E goes up. If D, thank you. If D goes up by just a little bit, that means that E will go down by a lot, because it's an inverse square relationship. So for example, if I double D, I quarter E. If I triple Q, I triple E. That sort of thing, just like we saw in Coulomb's law. Now, electric fields. So go back to our original plates. We'll see this later with cells. If I go back to my original plates, I have a positive charge over here, I have a negative charge over here. And what we're going to see with cells is that we'll have a cell membrane, and on one side of the cell we'll have an excess positive charge, and on the other side we'll see an excess negative charge. And so we'll get a similar thing in what we have here. There is an electric field between these two plates. What is the direction of the electric field? Is it left, right, up, or down? Let's try it as a quicker question. What is the direction of the electric field at some point in between those two plates? A, left, B, right. It's either left or right. Which is it? You know it's not up or down. Is it A, left, or B, right? What is the direction of the electric field? And remember, that's going to be the same direction that a positive particle will feel a force. So that's really the question you're asking. If I have a positive particle in between these two plates, what is going to be the direction of the force? And that'll be the same as the electric field.
Okay, so you're always assuming the extra one is positive.
Always a positive test charge. Always, that's what you always carry. That's the question. What is the direction that the positive test charge would go? All right, let's stop at 45. 45. All right, very good. So I imagine a positive test charge. We've already seen this, right? That it would feel a force that's in that direction. That would be the force. That means that my electric field is in this direction. So the electric field in between these two plates with charges on them is going to be in that direction.
So since you're assuming that that was always going to be direction, was always positive, it's never going to move in another direction.
My electric field will never move from negative to positive. That's just not how I define electric field. All right? It's always like this. Always from positive to negative. Now, not always straight lines, electric fields. We can have, we're not going to get to this, I don't think. And we don't do this, but let me show you. You don't need to write this down. Let me just show you. Say I have a positive particle and a negative particle. The electric field for this looks quite a bit different. This is called a dipole, right? You'll probably study dipoles in physical science because they're fairly common in chemistry. In this one, my electric field looks like this.
That's what I was wondering. It's like you had the thing going this way, and I was like, wait, what positive was to the negative? Okay.
All right. When I'm in between the two particles, directly in between them, as I am in the plates, it just moves straight across. And so this electric field line is like these. I have electric field lines that move across. But when I move out into space, the electric field lines begin to curve. Okay, and when you begin to look at these things like this, it makes it much more powerful and allows you to describe the directions and the forces that particles will feel when they enter into an electric field. So imagine if I take a positive particle out here, say I have a positive particle here, well, it's going to feel a repulsive force from this particle, and it's going to feel an attractive force towards this particle, so the net force that it feels will be in that direction, which is the direction of the electric field. Okay? Again, we're not going to see 2D fields. We'll just deal with the 1D field. I just want you to have a conceptual understanding of what they are. Because the cell is basically a 1D field. There's not a whole lot of funky electric fields that go like that. All right, so charges produce fields. And then also, a force acts on a charge in an electric field. Charge. In an electric field, an E field. So, if I have a positive particle here, it creates an electric field. It looks like this. Goes out radially in all directions, like that. And then if I put a particle inside of this electric field, it's going to feel a force that's in the same direction as that electric field. These are sort of the big ideas. That charges produce these fields, or really it's that we use fields to describe the effect of charges on other charges. And then a force acts on a charge in an electric field. Vanessa, you raising your hand?
Oh,
no. Okay. Now, Jim, also remember, so the other big ideas that we had here were Coulomb's law, that if I have multiple charges, they experience forces. I also had the idea of electric fields, that's force per charge. And then we kicked around the idea of electric potential. We haven't seen that yet, but let's go ahead and put it in this energy per charge. You will certainly have a question or two that asks you to clarify these things. What is an electric field? An electric field is a force per unit charge. Or what is electric potential? That's energy per charge. You certainly have questions, just sort of asking for a definition of that. And then electric potential energy. We've seen this before. Right? We've seen potential energy before. We saw gravitational potential energy. That if I have an object, the Earth puts out a gravitational field, it goes straight up, it goes out radially, just like this. But with the Earth, the gravitational field lines are in what direction? Towards or away? Towards. Because if I put a mass here, it feels a force in the direction of the gravitational field. Similarly, if I were to put if this was a negative particle and I put a positive particle, it would fall towards the surface of the charge. What was my point? Oh, so this has potential energy. This has the potential for motion. If I let it go, it moves. That's what potential energy is, the potential for motion. And so, potential energy describes an object's capacity to do work. So, when this object moves, that means that not that the object is doing work, but something is doing work on the object. So if I let this go, the gravitational force does work on the object. Okay?
So, if there's a potential energy from electric, is there a kinetic energy from electric?
Yeah, we'll talk about kinetic energy. That when objects move in an electric field, they get kinetic energy. Yeah. It's all very similar. So, because charged particles experience forces, they have the capacity for motion, right? If I have a positive particle here, right, and there are the field lines. All right, now let's do a negative particle. If I have a negative particle, the field lines are in, like that. If I put a positive particle out here, it will feel a motion towards that negative particle, opposite or along the field lines. We can do this simple derivation. We can say that work is equal to force times displacement. And also by the work energy theorem, we can say that that's equal to our energy. And so this is U. We've used U once before. You might not remember. U is for potential energy. And so we'll use it here for potential energy. So it's equal to U. And so F is KQQ over D squared. That's Coulomb's law. Times another distance, because I have this extra distance out here. And that gets rid of that, and I get an expression for the potential energy, that is U is equal to KQQ over D. That is for electric potential energy. On your equation sheet again, you will need to know, we'll have some questions I'm sure about, how is the potential energy related to Q and D? And you'll need to look at, like, if I double this, what happens to this? Those sorts of questions. Okay?
Why does this square go away?
Because I canceled it with the D. I had a D in the numerator, and I canceled it with the 1 in the denominator. Yeah,
What
Alice.
is D?
What is that?
What's D?
Oh, D is the distance between the objects. I'm sorry. Yeah, so, well, actually, yeah, Alice, this isn't really a real equation. I'm just sort of doing a dimensional analysis. So just think of D as a distance. Yeah. And so this isn't a real derivation. I just sort of want to show you how the units work out. Is that clear? Does that answer your question? You sure? Okay. Yeah, D is a distance. It is on the equation sheet, yeah. So you don't have to know how to derive it. I just want you to sort of see it. It helps people sometimes. All right. So if I have two particles, say two positive particles, they're separated by a distance d, just like we had with Coulomb's law. They have the potential for motion, right? Whether they're both positive or both negative or one positive and one negative, If I have two particles and I let them go, they're going to fly apart from one another, or they're going to fly towards one another. Either way. So they have the potential for motion, and we describe that with this expression. Our potential energy is equal to that KQQ over D.
So you said we're not going to need to use like the equation, like plug in numbers?
No, you're not going to calculate anything. So here we can have either positive or negative potential energy. We didn't have that. We didn't really talk about gravitational potential energy in this way. We talked about it in a slightly different way. But with gravity, you can't have either positive or negative. You only have positives. Two like charges will have what? A positive or a negative U? If both Q's are positive, what does that make U?
Positive.
And both Q's are negative, what does that make U? Positive, right. So if I have a negative value here and a negative value here, then that means that U would be positive. So two like charges have a positive U, a positive potential energy.
So this is different than potential.
Actually, let's do work. Positive work. Yeah, this is different from potential. Be careful. Potential is energy per charge. This is potential energy. It's not the same as potential. Understand, you sort of get the words all mixed up in your head, but this is, yeah, we've already seen potential, but we're going to see it again. So two like charges have a positive potential energy or a positive work, and you have to do positive work to bring them together. Remember positive work? Oh, I'm sorry, we're out of time, aren't we? We go to 8:50?
Yeah.
All right, we'll pick up with this next time. Oh, your exams. You can pick those up on your way out.